Now we'll analyze series RLC circuit connected across an AC EMF. Here the three components are connected in series and the EMF is E0 sin omega t. We calculate the phasor current in the circuit for its analysis. First we need to calculate the circuit impedance. And here circuit impedance Z phasor can be written as R phasor plus XL phasor plus XC phasor. This we need to write. And here the values we already know Z phasor is R angle 0 degree plus is omega L angle plus pi by 2 plus XC is 1 by omega C angle minus pi by 2. If we draw the phasor diagram for calculation of Z, we can see the value of R will be taken at 0 degree. Omega L is taken at plus pi by 2 and 1 by omega C is taken at minus pi by 2. Here we can see if omega L and 1 by omega C are added, and numerically these will be subtracted and the resulting value will be somewhere here, which is having a phasor value omega L minus 1 by omega C. And when this is added to R, the resulting value will be in this direction, which is Z. And the value of Z can be given as root of R square plus omega L minus 1 by omega C square. And this angle theta we can calculate at tan inverse of omega L minus 1 by omega C divided by R. So here we can see the impedance phasor we can write as in magnitude root of R square plus omega L minus 1 by omega C whole square, and its argument can be written as tan inverse of omega L minus 1 by omega C upon R. This is the argument of this impedance phasor. And now we can apply Ohm's law for calculation of phasor current in circuit. And here phasor current in circuit can be given as EMF phasor by Z phasor. We substitute it as E0 angle 0 degree divided by the impedance phasor, which is root of R square plus omega L minus 1 by omega C whole square angle tan inverse of omega L minus 1 by omega C upon R. Now further simplifying the value of current phasor we are getting in magnitude, which is the peak value of current in circuit E0 upon root of R square plus omega L minus 1 by omega C whole square, and its argument is 0 minus of this, we can write it minus of tan inverse omega L minus 1 by omega C upon R. Here this negative sign can also be taken in and we can write it 1 by omega C minus omega L. So here we can see if omega L is more than 1 by omega C, current will lag behind EMF. Which is obvious because if we are taking the effect of ohmic opposition of inductor is more than that of capacitor, current will ultimately lag behind. And if 1 by omega C is more than omega L, numerically a negative sign can be taken out and this will be positive. And we can say if capacitor will have more ohmic opposition or its reactance is more than that of inductance, then the current will lead EMF by this angle. Now in this particular situation we can also write down the time function of current, which can be given as E0 by root of R square plus omega L minus 1 by omega C whole square sine of omega t minus tan inverse of omega L minus 1 by omega C upon R. This is the time function of current we are getting, and whether it will lead EMF or it will lag behind EMF will depend on the magnitudes of omega L and 1 by omega C, whichever is higher. That will decide the sign over here whether it is leading or lagging. And similar to the previous cases, here also we can draw the phasor diagram. EMF will be at 0 degree and current in this specific case I am taking that this I0 is lagging behind by this angle theta. but it may be positive if 1 by omega c is more than omega L. In next section, we'll study about the phase relationships in series RLC circuit also.